So we started off today with a little activity. Obviously, it was class data, so if you are not here today, you can't do the activity, so we'll just start from here. But we made a dot plot of some information, and they asked us to, like, describe the shape. Here's what you got to look for when they ask you, hey, what shape does this data look like? You have to look for major peaks, right? You have to look for major peaks, not minor ups and downs in the graphs. Can you kind of tell with these dot plots that I have already, like, here's a major peak right here. Here's a major peak. Here's a major peak, major peak, major peak, where it got like really high, you know, or sometimes a really low valley kind of thing. Look for major peaks. That's something that we're looking for. Another thing we're looking for is clusters of values and obvious gaps. Clusters of values and obvious gaps. And then we got to decide if the distribution is what's called roughly symmetric or clearly skewed. And that's what we'll talk more about here in a second. So is it roughly symmetric or clearly skewed? And let's go back to our data and look at it. Do you feel any peaks? Where would there be a peak if you see any? At 12. Are we cool with that? That's like the highest that it gets. Cool. Are the dots to the left of 12 like evenly balanced with the dots to the right of the 12 or not? Where are there more dots? On the left, right? So here's all different things that could happen. The first is like called roughly symmetric. Like I want you to draw the same thing I draw right here. If I was to draw like just a curve over the top of the dots, do you see how it like kind of almost makes like a bell shape? If you're with me on that. I want you to write that down. You'll see that on homework all the time. Is it like bell shaped? If I could write the word shaped. It's not like it has to be perfect, you know, but would you believe here was the peak, and it seems like there's about the same amount of dots on the left side of the peak as on the right side. It's not going to be perfect. That's why they say roughly symmetric. And then bimodal. Have you heard of like mean, median, and mode before? You know, mode means what again? If you're not sure, that's okay. Mode means what? How about mean? What does mean mean? Mean is that would be the median. The median is the middle. Mean is the average, and the mode is the most occurring. The mode is the most occurring. So, like, do you see, like, the peaks on these? There's 2 of them, right? How about a bicycle? How many wheels does that have? 2. So bimodal means there's, like, 2 modes, right? Bimodal. Modes is what appears the most, so do you see that that has, like, 2 peaks in that case? Let's draw this curve anyway. I like to just kind of think of it like this. Is, all right, that peaked twice. That is bimodal. You don't see too many of those in the data that we're going to study. I mean, it happens, but it's just probably not that big of a deal. Roughly uniform. Isn't that pretty flat? You know, there was no real big peak that stuck out at us. It's not perfectly flat. That's why it's roughly, but it's just like, hey, it's kind of like everything showed up about the same amount of times. But here's stuff that is kind of weird at first. Let's draw this curve right here. And check this out, man. Here's the peak, right? Where are there more dots? Interesting question, right? But do you see that the peak is farther to the right than it is to the left? So this is what's called skewed to the left. And a lot of people, for their first go-around, think that's backwards. It's like, isn't it skewed to the right in that case? So let me ask you this. What if we took the average of our ages in here, but only students, right? What would that average roughly be? 14 to 15. Are you with me on that? So then what if I put my name in the hat, and I am 44 years old? Would that throw off the average, yes or no? Yep. And if I plotted it, like all your dots would show up around 14 and 15. Are you with me on that? Then my dot would show up at 44. So it would kind of look like this. You'd have this number line where it was like 14 and 15, and you'd have just dots galore, right? And then I have boop, 1 dot over here at 44. Wouldn't it make the data go? It would skew the data. Are you with me on that? Where's that dot at? On the right or to the left? Wouldn't it make the average of our age in here go up in that case as well? So that skews the data to the right because that's where there is a tail. Let me delete all this stuff. And how do you feel about there is a tail right here? That tail is on the left. And this dude right here, this is data skewed to the right because here is the tail. That's where you're going towards the extreme values, right? A tail. So let's try this again. What do you think about our data? Let me snip it out so I can like totally draw on top of it. If I could get there, let me snip it out. And where did it go, George? It didn't do it, so let me try that again. Page. I'll just do this, do what I always do. If I was to draw this curve right here, what do you think? Is that fairly symmetric, skewed to the left, skewed to the right, bimodal, or fairly uniform? Discuss. It's not that easy to see this because it's not that high of a peak. Are you with me on that? It's not that big of a peak, but I would call this data skewed left in this case. Skewed left. No big deal. We're still learning, you know. But let's get back to this. So we've got all our data. Let me see what we want next. So we got all that. Let's try this out. If they ever ask us to describe the distribution, we're going to do what I call SOCV. You see the S-O-C-V? I just call it like SOCV. It's an abbreviation for, we want to describe the shape. So that would be, hey, fairly symmetric, you know, skewed left, skewed right kind of stuff. That's the shape of a graph. Then the outliers is O, outliers. And then the center is for C. And then the variability is the spread, you know, the variability, which we'll talk all about all those things here in a second. So the shape, the outliers, the variability, and the spread. Median. Have you ever been on the interstate before? Where's the median? Median means middle, right? So you got to put all your data in a row, and just like if there was like 11 pieces of data, the median would be the 6th piece because it's like there's 5 on the left of it and 5 on the right if you put them in numerical order. So the median is the middle of a value in an ordered set of data. I'll bet you kind of roughly know what an outlier is. Like, what does an outlier mean to you? An outlier would be something that probably doesn't fit like the pattern, right, in that case. So an outlier falls outside of the overall pattern. That was when I was talking about our ages. If we put all of our ages into the applet and did the crunching numbers, my age would be an outlier. It does not fit the data, man. It does not fit the data. So let's do it, man. Here's a couple of dot plots going on about just some weird data. I know it's kind of strange, but it's like nitrates are organic compounds that are a main ingredient in fertilizers. So we know what fertilizer is. It makes like grass grow better and all that stuff. They put nitrogen in there, you know, aka some nitrates. When fertilizers like run off into streams, they can have a toxic effect on fish. So like, okay, they did all this, and then the rain happened, and then all that stuff went into the rivers, and it could do something bad to fish. So they studied all this in 2 different streams. One stream is called Stony Brook. The other one is called Millbrook. They just looked, hey, how much nitrogen is in these here streams right there. Describe each one of these guys with SOCV. So let's do this down the side. Let's put an S. Give yourself space to write a little bit. O, C, and V. S stands for the shape. Let's get good at this, man. It's going to take a little bit, but by the end of the assignment, we'll be okay. Let's go to Stony Brook, and let's draw this cool little curve right here. And then the same thing for Millbrook. So you talk to a neighbor. What do you think about Stony Brook? That's the top one that I have highlighted in green. Shape-wise, let's go through the big 3, and then sometimes it could be that fairly uniform or that like bimodal, but do you think it is fairly symmetric? Discuss with a neighbor on that. Do you think that Stony Brook is fairly symmetric? Okay. I don't think so either. So it's probably skewed. Where do you feel it is skewed? To the left or to the right? Here's the peak, right? Where's the tail longer at? On the left side or on the right side? On the right, so we're going to call this guy skewed right. Skewed right. Skewed right. Then what do you think about Millbrook? Don't forget, it doesn't have to be perfect, right? But let's go with the first one. Do you feel that this is fairly symmetric? I think so. The peak is pretty close to the middle. I know there's like more dots on the left side than on the right side, but I don't think tail-wise either one of them is longer than the other. Are you with me on what I'm talking about, the tail? So I'm going to call that fairly symmetric. It is definitely not perfectly symmetric. There's very few bits of data that are perfectly symmetric. That's why the word fairly is in there. So S stood for shape. What's O stand for? Looking for outliers. So again, there is a mathematical way to show that. We'll learn that later this chapter. But let's look at Stony Brook. Do you feel there's any dots that just don't fit this data at all? Not really. There is a small gap here, though. Would you believe there is a gap in the data right there? But those two dots that are to the right of that gap aren't that far off. So I would say probably not, right? So no apparent outliers. There's no apparent outliers. We can't prove that until we do the math on it. But as of right now, we'll just say, I don't think so. But what do you think about Millbrook? Do you feel that there are any outliers? Because there was gaps in the graph, and then there's some dots that are just way out from that. Do you feel that there are any outliers? Okay, how many do you feel? 2? Which 2? 18 and 20. So I'm going to put this. There's 2 possible outliers, 18 and 20. 2 possible outliers in 18 and 20. We'll prove that another day with mathematics. But today, we're just roughly guessing. It looks like 18 and 20 might be some outliers. C is center. If we have this data in the applet, the center is awesome to find because it is the median. I'm going to go back to our class data right here. Like, check this out. Would you believe they totally tell us the median is 9? Do you see where it says med, for median is 9? But we do not have this information in an applet, so what we have to do is find the median, which means middle. Go back into the question and pray they told you how many dots there were. Did they tell you how many dots there were? Yes, 42. I need to go in the middle of it. Take 42 and split it in half. What's 42 split in half? So I have to find the 21st dot. So how do I do it? I sit and count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Here's the 21st dot, if I could just highlight in a different color. But because there is an even number, you need to find the 21st and the 22nd dot and average them. But aren't they on the same value? What value is the 21st and the 22nd dot on the number line? 5, right? So the center of the Stony Brook is at 5 milligrams per liter. How did I get that label? Right here from the chart, right? It says milligrams per liter on the x-axis. See if you can find the center of Millbrook. There's still 42 places, right? So find the 21st and the 22nd dots. You count from left to right because aren't they in order on the number line? Right? So scratch them off like I did, scratch them off. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, and 22 are right here. One of them is 8. One of them is like a little more than 8. It doesn't even look like 9, So, but I would probably look at my choices and see which one is really close to 8. Does that kind of make sense? So I just put about 8.5 milligrams per liter. We don't have enough information to do the true math. It's like, well, where is that other dot at, You're probably thinking it's at 9. Maybe it's at 8.5, So if you average those, it'd be 8.25. But you're looking through your choices and seeing which one makes the most sense. How do you feel about the center of that? Let's do something different. What if there was 11 things on there? Which one would be in the center? Take 11 and divide it by 2. What do you got? 5.5, round it up, right? So the 6th dot would be in the middle because wouldn't there be 5 things on the left of it and 5 things on the right of it, right? So if you get an odd number, you will just have 1. Variability is basically this. How much does it vary? And what you do is you take the the range of those guys. You know the range is like the high and the low. So who is the lowest one in Stony Brook? 0. Who is the highest one in Stony Brook? 12. So here's what the variability is, from 0 to 12 milligrams per liter. They're just saying, how much does this vary? It varies from 0 to 12, right? It varies from 0 to 12. If I did that with heights, and the shortest person was 5 foot tall, and the tallest person was 6 feet tall, and there was all kinds of people in between, it's like, what's the variance? From 5 to 6 feet tall. You know, that's how we vary in that case. It's just your low to your high. So can we do that on Millbrook? What is the low on that one? 0. What is the high? Which one has more variance? Stony Brook or Millbrook? Millbrook varies more, right? So it's like a weird word, variance, but it's such a simple concept. It's just low to high. How much does it vary from? Are we cool with SOCV? Shape, outliers, center, and variability. If we put stuff into the applet, it will tell us the center because that is the median in that case. So, all right. So that was dot plots. Let's make a stem plot. Can you go back to Canvas? And here's the cool thing. I need to show you on homework how you can copy and paste your data. I think entering all this data is worthless. Usually when you get data, it has been provided in a spreadsheet already. When you take a survey for people, it usually goes in the back end in a spreadsheet. So if we go back to the agenda, you'll see a link on the agenda that says, like, data needed. I went ahead and put that into a spreadsheet for you. This is this data right here. Cool? Copy it. Just go in here, take it all, and Control-C. Copy that data. Then go back to your agenda and click on Applets. So copy the data. What kind of data was it? Did you copy numbers or did you copy categories? So we're going to do definitely some quantitative. And again, I'll always tell you which applet to use. We'll use the one quantitative variable single group, but not the collaborative one this time. This is you just doing it by yourself. So just click on this. Ba-boom. And see where it says data? Control-V. For you to put the data in successfully, you can copy and paste it. You notice that it just put a space in between them. Sometimes you'll put commas in there, but you can't put a combo. If they were separated with spaces, you got to do that consistently the whole way. If they're separated with commas, you got to do that consistently the whole way. But there is your data. Click Begin Analysis. Let's see what this data was about. First, let's do this. Let's describe it. What would you call that? Fairly symmetric, skewed right, skewed left, uniform, or bimodal? What would you kind of call that? Is there a major peak? No. It's pretty flat. Like the highest amount is 2 dots, then I would call that fairly uniform. Are you with me on that? What is the data about? It is about, like, just the resting heart rates of 26 ninth grade biology students. So we're in biology class, there's 26 kids in there, and they're just sitting there, and they measured their heart rates, right? It's their resting heart rate. It's not like they were doing sprints or activities, it's just your resting heart rates. So they say to make a stem plot of this data. Do you see that this is a dot plot, right? Stem plot, we're going to switch it to that, is this, to where we have the stems and the leaves. This guy right over here, we have to read this key. You see there is like numbers on the left. These are called the stems right here. And then the guys on the right are called the leaves, right? Sometimes they call it a stem and leaf plot. So let me kind of highlight over the top of this. They give you a key. You see that the 8 is on the left, and they have this little up and down guy, and the 6 is on the right. The 8 stands for 80. It could very possibly be like 800, 8 million, 8,000. You have to read the key, right? You know, so this 8 is 80, and then the 6 is 86. So I'm going to randomly point at some numbers on this stem and leaf chart and see what you think. What do you feel about this guy right here? This 1, what does it really mean? 61. Are you with me on that? What does this guy right here mean? 66. What do you notice about these leaves? Are they in numerical order or not in numerical order? Yeah, that's handy. Truth is, it doesn't have to be. It sure is nice if you put them in numerical order. That way you could find the middle of this with the median very, very easily. So let's see what they want us to do. We made the stem and leaf plot. I'm not going to ask you to draw it on paper, right? Don't need to do that. That's what the applets are for. It says, what percent of these 9th grade biology students have a resting heart rates below 70 beats per minute? You really don't need the stem and leaf plot to do that. You don't need the dot plot. But you see how this data is all over the place. You would have to hunt for all of those guys that are like less than 70. If we go back here, isn't it very easy to see because they are in numerical order already for us. So let me go back and see what they said. They said, is 70 count or not count? They say below 70 beats per minute. Does 70 count? Nope. So let's count up how many leaves there are. How many are below 70? There is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Do you see how I got those? Out of how many? You can tell right here because it tells you the total number in there. You could also tell in the question because they told you there was 26 students. So 11 out of 26, is that right? Dang it, don't have my calculator open. Could you please punch that in and see what 11 divided by 26 is? About 42 point what? So there, we got it all punched in, and it's about 42.3%. So we'll go back here and do that. About 42.3%. Let's describe the distribution with SOCV, right? So let's do the shape. What did we say? The shape would be what? Here's the crazy part. Which do you feel is easier to look at for the shape? The stem and leaf plot or the dot plot? So the cool thing is you can switch back to it, right? Isn't it easier to switch back to? What would you say on this? Fairly uniform, right? Or roughly uniform, whatever we said that was. So we'll call it uniform. Then let's do O, which stands for outliers, right? So I'm going to go back here. I personally think the dot plot is easier, but let's just look to the stem plot. Which one do you feel is easier to see the outliers? Either one, right? Do you feel that there are any outliers? Yeah? Isn't it easier to see the gaps on the dot plot, right? You know, so which ones do you feel would be outliers? You can also do a hover over, and it will tell you what that value actually is, right? So do you feel 48 is an outlier? What about 85? Or excuse me, I guess it's 86. What do you feel about that one? I'd say those are possible. It's your opinion right now because we haven't done the math behind it to see if it truly is an outlier. But let's just kind of put that. Let's just do possible outliers. Something, 48. And I thought the other one, 86, could be an outlier. If you don't feel that way, you don't have to put that. Center. No doubt about it this time. Let's go and use the chart. What is the center? It is the median of this data. So what would that be? This is the mean. We don't want that. Which one do we want? Median, 70.5. Cool. If we didn't have that, there's 26 bits of data. Would you believe you'd have to divide it by 2? You'd get 13. You'd have to average the 13 and the 14th guys together, right? So 70.5 beats per minute. Come on, man. 70.5 beats per minute. And then do the variability. That should be the easiest one. Low to high. What's the variability? From low to high. From 48 to what? 86 beats per minute. Stem and leaf plot. Things that need to be talked about, though, is what if I switch this back, what if, you know, like, see there's something in the 40s? What if the 55s didn't exist? What if there was no data in the 50s? Should the stem of 5 exist? The answer is yes. If the lowest number you got is 48, you would need a stem of 4. then you have to have a stem of 5, a stem of 6, a stem to get up to your high. So the stems have to be there. You would just have nothing in that leaf spot. It would just be empty. Does that kind of make sense? You need that because that really shows you there would be a gap there in that spot, right? So if you start a stem with a 4 and you need to get up to 86, you got to go 4, 5, 6, 7, 8. Is that okay? And then the last thing is the histogram. The histogram shows each interval as a bar. The heights of the bars are the frequencies of these relative frequencies in each interval. It took me a long time to know the difference between a histogram and a bar chart. People go, man, why is this not called a bar graph? Why is this called a histogram? We made bar charts last time. One of the bar charts looked like this. It was the colors of the cars. There was like blue and green and red and all of that stuff. What kind of data was that for that bar chart? Categorical. Bar charts are for categorical data. Everything you read on a bar chart on the x-axis is categories. It could be car color. It could be Republican, Democrat, things like this. You know, what's your favorite social media app? Instagram, TikTok, whatever. Those are categories, right? What kind of data is this right here? These are numbers, so that is what? Quantitative data, right? So you see what happens is if you had a dot plot, what they're trying to show you is, do you see all these dots right here are between 0 and 5? What they did is they put that in a bin. They said, okay, we can go between 0 and 5, and there's all those same dots, and then they just made a bar out of it in that case. So that was like every data point between 0 and 5, right, in that case. And then the interesting thing is, where does 5 count? Does 5 count or does 5 not count? In a histogram, the number on the left is in your bar, right? So in this axis right here, do you see 0 is on the left and 5 is on the right? 5 is not in that bar. Are you with me on that? So what do you think about this guy right here? Is 15 in that bar? Yes or no? Yes. Is 20 in that bar? No. So the guy on the right is not in the bar on the histogram. So what they got for us is to totally make a histogram of all of this data. Slideshow. So what are histograms most useful with? You know, large data sets. Large data sets. And the intervals are sometimes called bins or buckets. But put this at the top to remind you that histograms are really used for quantitative data. Histograms are really used for quantitative data. So to put all this stuff into the applet, when a spreadsheet is provided or homework has it, you can copy and paste the data from your homework. You would only have copied the ages. These are all the presidents of the United States of America, the first 45. You know, you can see that Biden is missing from this list, and then Trump again, right, because Trump is the 45th and the 47th president. But the first 45 presidents, this is their age when they took office, when they were totally sworn in, right? So what you'd have to do is just copy and paste all the ages. Let me show you what that looks like. So if we copied and pasted all that in, that's what the histogram would look like, right? Sorry, I just kind of switched screens on you right there, but that's the histogram. Let's describe the shape of it. You tell me. Do you think that's fairly symmetric, skewed left, skewed right, uniform, or bimodal? What would you call that? Tell your neighbor. What do you think? I would call that fairly symmetric, right? So that is fairly symmetric. So that's what we're going to do. Fairly symmetric. It's on the right side of that chart that you're giving you. I kind of snipped it out. Did they ask you that on this or not? Nope. I wanted to do it anyway. So we made that. Your question on your worksheet says, what % of the presidents took office before the age of 60? Is that the only question you got? So I just think it's good to always describe the shape. Before the age of 60, right? So let's read this guy. Here is 60 on the number line, right? Question, this bar right here, does 60 count or not count? 60 counts. But they say before the age of 60. What do you think about this? Does that bar before the age of 60? This one before the age of 60? This one, this one, this one. The question is, does that one count? Are those presidents who took office before the age of 60? Remember, 60 is in that bin. Do we use that bar or not use that bar? Not. So here it is. How many are in there? It's tough for you to see, I know. There is 2. There are 4 right there. There are 9 right there. There is 11 right here. And there is 8 right there. Are you cool with that? Please add those up for me. That's how many presidents were in those bins right there. And tell me what you get. How many? 34. Do you know how many total presidents there are in this chart? It tells you in here how many total presidents are there. So 45. So I didn't have to add the rest of them up. 34 divided by 45. About 75.6%, right? About 75.6%. Just for fun, does anybody know who the youngest president is without having to look at the charts? This is JFK. JFK was the youngest. Roosevelt was close, right? But JFK was only 43. So, cool. That's the lesson today. Let's see what you think. Let's try some homework.